In this video, which is a follow-up to the previous one, we're going to calculate the shear stress and the normal stress in a bar with an oblique cut. Whereas in the previous tutorial, we made the vertical cut for the bar, this time the cut will be made at a 30-degree angle to the vertical. And if I say that we're gonna make a cut, don't take that statement too literally. What I mean is that if you really have a bar that is subjected to a tension force and you make a cut through it, then you're gonna end up with two pieces of the bar, and those two pieces will be separated further apart with no forces whatsoever acting on the cutting areas. So if I say that we're gonna cut the bar and we're gonna determine the stresses, I mean that yes, first we are gonna cut the bar, but then you can think of as gluing the sliced pieces of the bar together, and that allows us to calculate the forces that act on the cutting areas. As I said, this time we're gonna make an oblique cut with a 30-degree angle to the vertical, and the 30-degree angle is referred to as alpha. Alpha is the angle towards the vertical, as I said. So it is important to mention that the angle is in reference to a vertical axis, because sometimes you could also think of the angle as the angle towards the horizon. So by definition, in these situations, alpha is the angle towards the vertical. And our goal is to calculate the normal stress and the shear stress. And to do so, we're gonna again rely on the equilibrium conditions. One convenient way to set up the equilibrium conditions is to establish an axis system that is aligned with the normal force and the tangential force. And such coordinate system is shown here. As you can see, that coordinate system is rotated counterclockwise by 30 degrees, which is consistent with the angle towards the vertical. And if we have that coordinate system, the normal force will be aligned in the x direction, as shown here. That's my normal force. And the tangential force will be aligned with the new, or let's say the rotated y-axis. And the y-axis is pointing to the southeast. The force F, the tension force, still acts horizontally to the left. And I'm gonna draw the tension force in as well, the way it is. So that's my tension force. And let's start setting up the equilibrium condition for the x-axis. I'm going to draw an arrow to the northeast. And that arrow not only means that we are setting up the equilibrium condition in x direction, which points to the northeast, it also means that if the force points to the northeast, the corresponding magnitude is treated positively. So along the x-axis, we have the normal force, which is positive, and in the negative region, we have the x component of the tension force. And the x component of the tension force, let me visualize it. So if I draw an accelerated line here with the right angle, this component, which points in the negative direction along the x-axis, is going to be my x component of the tension force. And that x component is simply equal to F times cosine alpha, or in our case, cosine 30 degrees. Why? Because this angle is basically alpha, and alpha is 30 degrees. So N, and now we have minus F times cosine 30 degrees. And why minus? Because the x component of the tension force acts in the opposite direction of the normal force. So that is equal to 0. And if we do the math, we have the normal force is equal to fx, no, not fx, sorry, that's a multiplication sign here. F times cosine 30 degrees. And that is equal to 17.32 Newton. The tension force is the same as in the previous video, 20 Newton. Likewise, the diameter of the bar with a circular cross-section is 10 millimeters. Now, let's do the equilibrium condition for the y-axis. In that case, I'm going to use an arrow that points to the southeast. And for the y-axis, we have T, which is the tangential force. Tangential because it acts tangential to the cutting area, or parallel to the cutting area, minus, okay, let's determine the y component of the tension force. The y component is here. Well, it's not quite straight. So, okay, and this is my y component of the tension force. And Fy, if you do the trigonometry, you will see that this component, sorry, I'm gonna use a different marker here. So this force component is equivalent to the tension force times sinus alpha. So T minus F times sine 30 degrees is equal to 0. And if we rearrange this equation, we're going to have T is equal to F times sine 30 degrees, and that's equal to 10 Newton. The sine of 30 degrees is 0.5, and 0.5 times 20 Newton is equal to 10 Newton. Okay, are we ready to calculate the stress values by plugging these values into these equations? Not yet, because we need to find the cross-sectional areas where the stress or the forces are acting. And the cross-sectional area is different from what we had in the previous video. In the previous video, we made a vertical cut, and computing the cross-sectional area was quite simple. You just multiplied the radius to the square times pi. But this time, because the cut is made in an oblique manner, the area will be higher than if you made a vertical cut through the bar. So let me illustrate it here. If you make a vertical cut, let's say your area is gonna be this one, but if you make an oblique cut at an angle of 30 degrees to the vertical, you're gonna end up with a cross-sectional area, that is bigger than in the purely vertical case. So you could think of the vertical cross-sectional area as pi times r squared, and with the oblique cut, the cross-sectional area will have a magnitude of A is equal to pi times r squared divided by cosine of 30 degrees. Why is it necessary to divide the product of pi and r squared by cosine of 30 degrees? Because here we have a right-angled triangle with this angle being 30 degrees and the right angle being here, and cosine is the ratio of the adjacent leg to the hypotenuse. The adjacent leg is pi times r squared, and the hypotenuse is our new area that we're looking for. And the hypotenuse is therefore gonna be pi times r squared divided by cosine 30 degrees. So let's take the area of the oblique cutting area and plug it into these formulas. So let's start with the normal stress, which is equal to N divided by A. N has been computed before, that's 17.32 Newton. And the cross-sectional area, let's compute it in a separate step. The cross-sectional area is roughly 91.22 square millimeters. Okay, we're gonna plug that value into this denominator. And the normal stress turns out to be 0.91 Newton per square millimeter. So that's the stress that acts perpendicularly to the cutting area of the bar. And now let's compute the shear stress, tau, that's equal to T divided by A. T, in our case, is 10 Newton. And the cross-sectional area of the oblique cutting surface is still 91.22 millimeters squared. And that gives us 0.11 Newton per square millimeter. Okay, so that's the way to calculate the normal stress and the shear stress in the bar that has been cut at an angle of not zero, or at a non-zero angle to the vertical. Good. I hope we could clarify the principle behind calculating stresses with this video, and I would be happy to see you again. Take care.